All right, good evening, ladies and gentlemen. This is Petko, and welcome to Oratio Presents. This event, as always, generously supported by the European Space Agency and by Sofia Tech Park. They have accommodated us in this terrific studio, so we are grateful for their hospitality. So if you want to check out their spaces, come and look around. It seems to be very cozy. I mean, don't look at the black background that I have. It's much more colorful and nice in here. All right, today we have a space-related event. These are as popular as always in our program. So today we deliver one especially for you guys. Now, we all know that the universe is, made of countless of galaxies, stars, and planets. Alongside with some more exotic objects such as black holes, and many of these objects emit light across the electromagnetic spectrum. But because human eyes can only see visible light, astronomers had to build telescopes that are sensitive enough to pick up the whole range of different light waves that actually exist in the universe. So there is a hidden, invisible universe out there that speaks to us through wavelengths and frequencies we cannot see with our eyes. Or with regular telescopes for that matter, but we are nowadays in an earshot of, thanks to radio telescopes. They have allowed us to hear the secrets of the gas giant planets, the blasts from the hearts of the galaxies, or the last breaths of dying stars. Now, recent advances in radio telescopes have also enabled us, to dig in one of the biggest mysteries in the universe, dark energy, giving us, as a result, a mind-blowing insights into the origins and evolution of outer space. And today, to learn more about this extraordinary astronomy field and its breakthroughs, we have invited Professor Peter Gallagher, who is the head of astrophysics at the Dublin Institute for Advanced Studies. Peter, welcome to the show.
Lovely to be here.
How are you doing,
Delighted
Peter?
to come and talk about space science and astrophysics.
Well, very good. We're looking forward to your talk. Again, it seems like it seems to be like a fringe side of physics to some. Most people are interested in more, let's say, pop sci things. But in order for us to understand how important this field actually is and how important these instruments are for us, in order to get some insights into the universe, we are grateful essentially to have you here because you're one of the experts in the field. So we are very happy to have you today, Peter. Whenever you're ready, you can go ahead and start. And I'm just going to ask our audiences, guys, take some notes, and you can ask your questions on the web platform that we usually use on sli.do/slido. So listen carefully, submit your questions, and Peter, after your talk, we will be back with a discussion, asking the questions that people might have. So whenever you're ready, you can go ahead and start.
Brilliant, Petko. Thank you very much for that introduction. And I guess you're right. Astrophysics may be a little bit of a strange area of physics, but I think what it does is it gives you that view of the universe in a way that maybe some other areas of physics don't. But that said, the laws of physics that we learn about within our laboratories, within theory and so on, help us to literally illuminate how the stars work, how galaxies work, where the universe comes from, the origin of the elements. Where does hydrogen come from? Where does helium come from? How do you get carbon, nitrogen, and oxygen? Where does the iron come from? How does life ultimately come from? So I think what, for me, astronomy brings together so much of science, and then you need the engineering as well. And actually, this talk is not just about the science of astronomy, it's also about the engineering and the technology that we require. But welcome, everybody. I really am delighted to be here today. I'm sorry that I'm not in Sofia with you. I actually first went to Bulgaria in 1998 to see a total solar eclipse when I was a PhD student, and I went up to Varna, and there was a Bulgarian Air Force base, and we observed a total solar eclipse, and we got some nice data. Actually, it was 1999 now that I think about it, August 1999, and we got some lovely data, and I even wrote a scientific paper with data taken from Bulgaria. So I have a long connection to the country. And before I start, I just wanted to welcome you all, but most especially I'd I'd like to welcome the Irish ambassador to Bulgaria and the Bulgarian ambassador to Ireland, who are both listening into this talk. So welcome to both of the ambassadors. Okay. Today, though, or this evening, I'm going to talk about this, what we see in the night sky. Every time you go out to the countryside and away from the bright city lights and you look up, you see the night sky and you see these beautiful stars. And splitting the sky in this picture is the Milky Way. And the dark bits are what we now know to be clouds, but, you know, clouds of gas and clouds of dust. But as a human being, we want to know, what are they? What are they made of? And this is what this talk is about. It's about us as human beings trying to understand these stars and these gas clouds. And where did they come from? You know, simple questions that a kid might ask you. Where do they come from? What are they made out of? Who made them is a question that I regularly get. What made them? Where are they going? Did they always shine? Will they always shine? Or will some of them explode? So there are lots of questions that we astrophysicists spend our lives trying to work out. Of course, to do that, though, our eyes just aren't good enough. You can look up at the night sky down the countryside or out in the countryside, but unless you've got a big telescope, or any kind of telescope, it's really hard to say very much. In fact, you can barely see the planets in our solar system. You can see Venus, of course, in the morning. You can see Jupiter and Saturn at different times during the year, but you can't see the moons of these planets. You can't see the rings of Saturn. You need a telescope to do that. So this talk will be about the technology, the telescopes, and the scientific discoveries that were made. And really a good place to start is back in the early 1600s with Galileo. And what Galileo did in 1609, around then, was he took a telescope, which was, of course, invented in the Netherlands, but he was the first one to really use it to study what he saw in the sky. And he did a couple of, and it is a very simple telescope. At one end of it is a lens, and at the other end of it is another lens, and then there's a tube. But even to make those lenses is a difficult job. The science, the technology that was required to fabricate a lens with the right shape that would bring light to focus. And then the understanding that when it's brought to focus, you need an eyepiece that's then going to allow you to see through the telescope. So what Galileo immediately did was he pointed it at the sun. A dangerous thing to do with a telescope, of course, but what he did is he realized that he could project the image onto a piece of paper. And these are the kind of pictures that he made. He actually drew these himself. And these are huge, big sunspots that he saw moving across the surface of the sun. And in fact, these are enormous sunspots. These are about 10 times the Earth across. So he was actually very lucky. There were very big sunspots that were visible at the time. But what was really striking to him is this sun isn't just this blob that doesn't have any features on it. There's actually features on it, and it's moving. It appears to be rotating. So for him, he began to think, well, hold on, this telescope has told me something about this object. It's not static, it's not stationary, and it appears to be rotating. And the question is why? He also then looked over here he looked at Jupiter. Here's Jupiter, and you can see that in the night sky. But with this telescope, he was able to see these tiny little pinpricks of light beside Jupiter, and these turned out to be the moons, some of the moons of Jupiter. We call them the Jovian moons. Europa is one of them. Ganymede, Callisto, and Io were the different moons that he was able to see. And every single night he watched them. And his conclusion was that these moons are moving around Jupiter. And I guess at the time, the consensus was, and it was kind of the Catholic Church consensus, or led consensus, was that we were the center of the universe. We were the center of the solar system, and everything rotated around us. But that's not what Galileo saw. And that got Galileo in a lot of trouble with the church at the time. But his telescopes led to these discoveries. And if you jump forward then just over 100 years, this is Herschel, German actually by birth, but went and lived in England, in southern England, and he built a telescope at Slough. And this is his telescope. It was 40 feet long, so you can divide by 3 to get it into meters. But it was an enormous telescope that rotated around, and at the very top, it caught light and brought the light down to the very bottom where there was a mirror, and he made his own mirror out of a particular type of metal. And then that brought it to focus where the observer was in this box, and he was able to then see with greater detail than anybody else had ever seen before. And this is Herschel's very famous telescope. These are some of the pictures that he drew. And you can see on the left-hand side, here's a comet, and he was able to see that there's a nucleus to the comet and there's a tail behind it. Of course, he didn't know that it was made out of gas at the time, and he didn't really know where it was going or where it came from. But these objects on the right-hand side were particularly interesting. When he pointed this telescope at what he thought were stars, it turned out that they didn't actually look like stars. They were elongated, or they were diffuse. They kind of looked like clouds. And at the time they were called nebulae, because they were nebulous, and they looked like clouds. But he didn't know, are they close to our planet, or are they far away from their planet? Are they in a galaxy, a cluster of stars with us, like the Milky Way, or are they many, many light years away? And of course, so that was a great conundrum of the time, is what are these objects made out of? Are they made out of gas? Are they made out of stars? And the next step forward then was, again, another 100 years later, until the Earl of Rosse, here in Ireland actually, built this so-called telescope called the Leviathan Telescope. It had a design similar to Herschel. In fact, Rosse as a child had gone and seen the telescope in Slough that Herschel had made. But Rosse had a lot of money, and he married extremely well as well. And his wife was also passionate about astronomy and creativity and science. And together, really, they built this telescope. It has a mirror at the bottom that's 1.8 meters long. And then the mirror, the telescope itself is about 16 meters long. So this was the biggest telescope in the world, built in the 1840s at sea level in Ireland. And between the 1840s and almost 1920, it remained the biggest telescope in the world. And every single night, the Earl would go up here with a big bearskin coat on him. He'd go up onto these galleries here and hoist himself right up onto the top. So this is basically 3 stories high, at 2 o'clock in the morning with the wind rattling. So it must have, he's a brave man. And he'd look through the eyepiece here and peer at these nebulae to see if the nebulae were made out of gas, or were they made out of individual stars. And he was the first person to make this profound discovery. And here it is. This is a drawing from the 1840s by the Earl of Rosse in County Offaly in Burcastle. And what you can see is these nebulae aren't just clouds of gas. There's actually some structure to them. It looks like a whirlpool that you'd see like in the bathtub as the water goes down the bath. In fact, we believe that the third Earl was actually looking down into a river that went past the castle called the Camcore River, and there was swirls in the river, and he named it the whirlpool because it looked like those whirlpools in the river. But it told us something, that these things are far away, and these things are actually moving. And in fact, they're made of tiny little stars that you can see indicated here. What he didn't know at the time is actually there was 2 companion galaxies here that were interacting with one another, and gravity was pulling material one from the other, and it was swirling around. But it made the universe bigger. It gave us an insight into the structure of the universe, just because he had this big telescope. And that's the way astronomy always works, or generally works, I should say, maybe not always, very strong word. But generally, big telescopes and big instruments are the things that help us make discoveries. Now, if we jump forward into the 1980s and into the 1990s, the European Space Agency and NASA built a satellite with a telescope on it, very much like the Leviathan of Spur, called the Hubble Space Telescope. And they saw the Whirlpool Galaxy as well, but in a new light. And it looked like this. And just, even if you don't like astronomy, it's just beautiful. It's a beautiful, beautiful structure. But now we know that there are stars within it, billions of stars in it. We also know that there's a black hole at the center of it, and it's what all of these objects are swirling around. Of course, the third Earl of Rosse didn't know that. There's little red blobs here with hydrogen gas in them. There's dark channels here with dust clouds that are obscuring the light from behind. But if you look and blink back and forth, the third Earl of Rosse in the 1840s didn't do too badly at all. Now, if you jump forward again from the 1840s right through to the early teens, 1917 or so, the Americans then built a telescope that had 100 inches in diameter. This was built by Hale. And again, Hale, actually, it's interesting. Hale was a great man at raising money, but also was a great astronomer as well. And actually, if you want to build big astronomical facilities, fundraising can be an important quality to learn to convince governments. And in Hale's case, a lot of those who in the Industrial Revolution and the railroads had made fortunes invested or supported these great telescopes. So here's the Hale telescope, again quite similar. It's a big light bucket with a mirror at the bottom, and then light goes into an observer's box where they can then look through it. And in fact, at this stage, they were then taking photographs of it, and they were taking spectra of it. And that is another powerful step forward in technology as well, that you can now begin to take spectra. And with spectra, you can do interesting things. You don't just see the objects, you can work out how dense it is, how hot it is. You can work out how it's moving through the Doppler shift. You can work out the magnetic field, and magnetic fields are really important in galaxies as well. And these are the kind of things that he did. I mean, if you just look out now into the universe with telescopes like the Hubble Space Telescope, you see just a small patch of sky is just covered in galaxies. And remember, each of these galaxies has billions of stars. I mean, it's incredible. I think there's 100 billion, so 10 to the 11 stars in one of these galaxies, and there are 100 billion galaxies out there. So there's 10 to the 11 galaxies. So that's 10 to the 22 stars in our universe, we believe. I mean, just mind-blowing numbers. And then if you start thinking about life, what are the odds of life in that? I would say pretty high probability of there being life out there. Maybe we could say that there's a certainty, but we haven't found them yet. And maybe that's the great quest of our lifetime, is to find life in the universe, or evidence for the life in the universe. But what Hubble also did was he measured the speed of galaxies, and he measured how far away galaxies were. And he found that there was a close relationship between them. That meant that things that are far away are going fast. Things that are close are going more slowly. And he was able to show that the velocity then is related to the distance, and it's related to this constant here. Now, if you don't like maths, doesn't matter. The H there tells you the age of the universe. He was able to work out the age of the universe. I've read his paper many times. It's only 3 or 4 pages long, but it's amazing. He measures this distance and speed. And then imagine when he went through the calculations, went, hold on, from measuring the distance and the speed, I can measure the age of the universe. I mean, what a profound insight from having a big telescope and the new technologies that were available. But you can't just keep building bigger telescopes. Number one, they get more expensive. And number two, they tend to fall apart because they're just too heavy. And this is a fundamental equation. And actually, it's funny, I probably shouldn't show any equations, but I do like them. And I'm sure some of you do like them. But who was it? I think it was Stephen Hawking said, his publisher said when he was writing Brief History of Time is, for every time you put in an equation, you lose half your audience. So I hope that you're still with me. But the important thing to say in this equation is that if you want to see small things, that's what small things are over here, delta theta. And over here is the wavelength of light that you're using and how big your telescope is, the diameter of your telescope. So if you want to see small things, you need a big telescope. And so this is what this shows you over here. Here's a small telescope, and it's say, for example, you had 2 stars. You just wouldn't be able to distinguish between the 2 stars. But if you got lots of government support and philanthropic backing, you can build a big telescope, and then you can see 2 stars. Or maybe that could be 2 planets, or maybe it could be a planet and a star that you're trying to resolve. And this is called the Rayleigh Criterion. But this wavelength thing in here causes all kinds of trouble for us, because it means if you go to longer wavelengths, if you build radio telescopes, then this number here has to be even bigger to get that one smaller. So this causes a trouble for radio telescopes. So we have to build huge radio telescopes in order to try and work out what's going on to get that smaller. So here's a big telescope. This is where humans go into. This is a tiny little thing, but this is the Lovell telescope in the UK, and this is kind of as big as you can build them. They just start falling apart at that point. And this led to a new technology development called a phased array. And here's a beautiful example of a phased array. This is Dame Jocelyn Bell Burnell. Well, she's Jocelyn Bell Burnell. She's now a dame, and she's a professor. But she built this radio telescope along with her PhD advisor in Cambridge, Anthony Hewish, and they were. The thing with this is they're just wires on sticks effectively, but you could spread these wires out over large distances, and you could collect all their signals and then let a computer do the work. So you're effectively building a big telescope. And in the 1990s, the Dutch got this idea that, hold on, why don't we just start spreading these out across Europe? And they conceived of a thing called the International Low Frequency Array, or Lofar. And then others, the Swedes and the Germans, out to Poland nowadays, the French and the British all got involved in this and built a telescope that basically was reaching its arms out across Europe. Now, it's a weird looking telescope, and here's what it looks like in the Netherlands. A very Dutch view, I must say, with the canals here. But these are the telescope bits and pieces. These are the collecting pieces of the telescopes. And actually, all of the data goes back to a supercomputing in Groningen, where it actually makes images. And this is the telescope. The weird as it may be, they're just wires, cheap wires, but because they're cheap, you can get lots of them and you can spread them all across Europe. And there's a little preamplifier in there that takes the weak signals and makes them strong. And these cables here are the antennas, the wires that pick up radio signals from right across the universe. And so that's why we don't want people with mobile phones wandering in around our around our fields or with any type of electronics. They're very, very sensitive. They're called the low band antennas. Excuse me. They pick up radio waves just below FM radio, so at 10 to 90 megahertz. And then these are the high band antennas, and they pick up radio waves above FM radio between 110 and 240 megahertz. And these are just wires again in here that are held up by styrofoam, so they're very cheap. And in fact, they were called the IKEA flat pack of radio astronomy, and they really are like a kind of an IKEA piece when you get them and you put them together. So we in Ireland saw this happening, and the Europeans were spending 150 million euros building this big radio telescope, and we wanted to be part of that. So we put together a consortium, and it included all the major universities in the Republic of Ireland, plus also Armagh Observatory in Northern Ireland, and we formed this consortium. And we got backing from everybody from, the local kids collected money for us, but then, the local county collected donated money. But then the government came in through Science Foundation Ireland and supported the telescope. And we spent 2 million euros building the telescope. Now, I thought this was a great opportunity to give young Irish, well, not just Irish, in fact, people an opportunity to come and build the radio telescope with us. So we put out a job advert saying, want to build a radio telescope in Ireland this summer. And we hired a whole group of about 23 students from America, from the UK, and one from Bulgaria as well. Janine, I don't think she's in there. She did her PhD in Armagh afterwards. And where else are they from? Actually, the ambassador to Bulgaria, that's her son there. This is Anton Afini Johansson, and he's actually doing a PhD now in Lofar. So a lovely connection between Ireland and Bulgaria there in radio astronomy already. But these poor students had first-class honours in physics and engineering and so on, and they went about digging holes in a field in County Offaly, laying cables, and they laid hundreds of kilometres of cables. This is Diana Morrison, who's now a research fellow in Finland, and here she is wiring up the antenna. This is Aoife Ryan. She's a PhD student now of mine. This is Pierce Doherty, it's not Pierce, Doherty. I've just gone blank on Pierce's name. Pierce is now a PhD student. And here he is working on the Pierce Murphy. Gee, good God, I was just talking to him an hour ago. Okay, and these kids are building the radio telescope. What a great opportunity. And here they are putting together the antennas. And after 3 months of sometimes sweltering heat in the summer in Ireland, sometimes lots of rain in the summer in Ireland, we had this beautiful object here, which is the radio telescope called Lofar. It's about 2 football fields apart, and it has lots of these wire antennas that I showed you earlier. It collects the antenna, the cables, the data through the cables, puts them into this box here, which is a shipping container, and then it goes on a fiber optic cable off to the Netherlands to be combined with all the data from across Europe to make pictures of stars, of galaxies, of explosions of the sun, looking for exoplanets, maybe even looking for technosignatures from life somewhere else in the universe. It was a nervous time when we came to turn it on. You know, you kind of expect smoke to come out of the back of this box, but it didn't. And this signal was received huge cheers. What it shows is shortwave radio communications down here, and then a lovely flat spectrum coming from our telescope saying, it's on and I'm working. And we all had a very big cheer and a couple of beers actually that night. And it was great celebrations in one of the local bars in Spur. With this telescope, though, you don't just see this spectrum. You get to make pictures. And this is a picture taken in July of 2017 of the radio sky above Spur. And this is invisible. As Petco mentioned earlier, it is an invisible part of the sky. But it's a great telescope for Ireland because you can see through the clouds. You can see if it's snowing. It doesn't matter. We see through it. And what we were able to see is the Milky Way right across the sky. But these blobs here were then objects that are well known. So we went and we looked, and there they are, exactly where they should have been. So this one here in the north is called Cassiopeia A, and it's a supernova remnant. It's actually a star that exploded, and it's still glowing at low frequency radio waves. This object here is one of the other great bright objects in the sky. It's called Cygnus A, and it's a radio galaxy. So we were nervous, but they were exactly where they should have been. And then you can see the Milky Way glowing across the night sky as well. This is called the Great Northern Spur, which is, again, an ejection of hot gas from a supernova. But the bigger your telescope is, the better you see. And so what we did is we took all the data from Spur and from Chilbolton, England, down to France, to Nancy, just south of Paris, right out to the Netherlands. And then you can put together a bigger telescope, and then you can start making even finer detailed pictures. And this is the kind of picture that you can then do. You can see we can zoom in on one object in here, say this on Cygnus, and you can see this kind of object here. And what you're seeing is jets, enormous jets that are hundreds of light years, 200, I have it written down here, these are 200 light years across. You have a black hole in the center that's billions of times the mass of the sun. You have an envelope of hot gas around it that's glowing in X-rays. And so Lofar, together with data from spacecraft, can give you a really comprehensive view of what's going on in a way that you couldn't do in other ways. Now, I'm obsessed with the sun. Black holes are wonderful, but I'm obsessed with trying to understand the sun. And this is a movie, if you wouldn't mind playing it there, taken by a spacecraft called, it's the GOES spacecraft. Is that movie playing okay? I hope it is. But this movie here shows the X-ray sun. Actually, it's the ultraviolet sun. And what you can see is an explosion happening over here on the right-hand side. And this is what I'm interested in. But these don't just emit X-rays. They also emit ultraviolet. They emit optical light, and they emit radio waves. So you can use radio telescopes to work out where these explosions happened, how they're happening, and also where the explosion, when the explosion happens, it sends out hot gas into space. And we want to know where it's going, because if it hits the Earth, it produces the northern lights, it produces the aurora borealis, and we'd love to forecast that. But also it can knock out satellites and have a variety of technological impacts. These are some of the data that we take. This is a paper led by Diana Morrison. She was my PhD student at the time, published in Nature Astronomy. But it looks weird, granted, but what it shows you is an explosion happening down here on the sun, a big blob of radio waves happening. So it tells you that there's a shock wave accelerating electrons and producing radio waves. And Lofar is able to tell you where that's happening in a way that another telescope couldn't do. And over here on the right-hand side is the stuff that I get excited about. But what it shows you is minute by minute, second by second, there's lots of bursts going on, tiny little explosions that are happening in the sun as the big explosion is happening. So the big explosion is happening, it's sending a shock wave out through space. And as it's moving through space, the shock wave accelerates electrons, and then these electrons go zipping off into space and they create radio waves. And with the Lofar telescope, in combination with these other spacecraft, we're able to work out where the explosions happen and where these electrons are going in space. And we care about that because some of those electrons will come towards us here on Earth, as I mentioned earlier. Now, we don't use these observations in isolation. We use other spacecraft together to try and get a comprehensive view of what's happening in these astronomical objects. And I think one of the most exciting spacecraft is called Solar Orbiter, and this is one that I'm involved in. It was actually launched this time last year by NASA. It's built by the European Space Agency. Actually, the heat shield here was built in Ireland by a company called NBio. And then you can see all of these little detectors on board with cameras. And there's an X-ray camera that we're working on called STIX, and it'll tell us about X-rays coming from the sun. But what's cool about this spacecraft is how hot it's going to get, because it's going to fly into the inner solar system to get pictures up close and personal with the sun. And actually, if we go on to this next slide here and play the movie, it was launched almost exactly a year ago. From Cape Canaveral. I actually got to go and see that launch, my first launch that I've actually ever been to. And as it went off, it then went through space. It took a left-hand turn, I guess, at Venus. So it did a gravity assist with Venus just Christmas past. And then it'll do another couple of swing-bys of Venus and of the Earth and of Mercury, and it'll work its way in until at a certain point it's getting to about a third the distance from the sun to the Earth, and that's the closest these kind of ultraviolet and X-ray cameras have ever gotten to the sun. But it's going to be hot. It's going to be hundreds of degrees Celsius in there, and the heat shield will protect it. But the cameras will be making important observations. And what me and my team are doing is we're coordinating those observations with Lofar. And Lofar is telling us about the radio waves that are being emitted, but STIX and the other instruments on Solar Orbiter are showing us exactly in detail where the explosions are happening. They're also measuring particles coming past the spacecraft as they move through space. So we get a really detailed view of what's going on in the sun and how the sun can then affect us here on planet Earth. Now, of course, we do some more exotic kind of observations with the space with Lofar. This was a very exciting moment, and one of the great discoveries of radio astronomy are pulsars. So here's a pulsar here, and really what it is it's a star that's about the size of Sophia in diameter, about the width of Sophia. It's about 10 kilometers across. Excuse me, and it's rotating many times per second, and it has a magnetic field, and it has a beam of electrons that come out of its north pole and its south pole, and when that beam of electrons moves outwards, it generates radio waves. So those radio waves are kind of like, it's kind of like a lighthouse in space for radio waves, and it's zipping around, beam, 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 and it's doing it so quickly that it's almost testing the laws of physics and general relativity. So it actually acts as a very accurate clock. And with iLofar, we were able to see these pulses, bing, 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 seconds go by. And that was a really exciting moment to see this. And a number of Nobel Prizes have been won for not only the discovery of pulsars, that Jocelyn Bell Burnell was involved in back in the 1960s, but also in contemporary tests for things like general relativity and time in the universe as well. Of course, Lofar had to go and look at some of the closer astronomical objects, and this is the Whirlpool galaxy that was named by the third Earl of Ross in Ireland. But what a radio telescope can do is it can look out along these arms and make more detailed measurements of what's going on in them. It can tell you about temperatures and density of the gases. It can tell you about the magnetic fields that's kind of holding up and structuring the galaxy. It can tell you what direction the magnetic field is going in, and it can tell you how strong the magnetic field is. And that really gives you an insight into what's holding up the gas in there, how's the gas moving, maybe there's star formation going on in there under certain circumstances, maybe there's planet formation going on in these galaxies. And also it tells you about how these galaxies are interacting with one another. Now, I put together this next slide, which shows you the Lofar observations. Actually, I should give credit to Sean Mooney, who was a PhD student, University College Dublin. He put together the Lofar image, and then over here, you can see the Leviathan image. Now, the Lofar data isn't necessarily as pretty, but it tells us a lot more about the physics of what's going on. And that's what radio telescopes in combination with optical images can do. Now, I mentioned one thing about these galaxies is, in order to keep all this stuff, these billions of stars moving, there must be something very heavy in the center of it. And what Einstein's theory said was, if you have these very dense, compact objects in his general relativity, that after gravity has collapsed and pulled things together, not even light can escape, and that's called a black hole. And a black hole is just one of these things that, certainly when I was a kid, it was almost like an unbelievable object. It was something that was in the textbooks, that although maybe we didn't really believe that it existed. And this is the kind of picture that many of us had in our minds from reading books like Brief History of Time, or listening to Roger Penrose, or even watching sci-fi movies. There was this kind of dark area where no light was emitted. There was all this hot gas spiraling around it. There was this thing here, which was kind of the last surface where no photons could ever escape again. And this is called the event horizon. Of course, gave rise to a movie. And there was a jet of relativistic particles, relativistic electrons, that then moved out at nearly the speed of light. And in fact, it's these that emitted radio waves, and we could see these with radio telescopes. But nobody could see what was going on in here because, number one, it was really, really small, but also they're very, very far away. These things are very distant in the universe. Of course, there is one in the center of our galaxy in Sagittarius, Sagittarius A, which is kind of down on the southern skies. In August, you'll see Sagittarius come up over. Of course, you're luckier than we are in Bulgaria that you'll see it rising higher in the sky. But in Ireland, we'll see it just above the horizon. But you need to build big telescopes, really, really big telescopes, to see these kind of objects. And this is what led to the Event Horizon Telescope. So if you wouldn't mind just playing that movie. So this is the Event Horizon Telescope. And what you can see is it's a telescope, not the size of a continent like Lofar is. It's a telescope, a network of telescopes that's the size of the world. And you can see there's telescopes in America, in North America, in the United States, coming down through Central America, down to South America, and then across here to Europe as well. And all of these telescopes, I presume that's in Hawaii, all of them working together, collecting signals, and then they bring all the data together at a supercomputer, and then they make images. And they make images that give us an insight into these black holes. Now, before we had the Event Horizon Telescope, which, is a telescope that's thousands of kilometers, actually it's megameters across, this is the kind of picture that we had of where we thought black holes were. This is M87. That's just the name of the galaxy. Not a particularly romantic one, but it's an elliptical galaxy. But there was this tantalizing jet coming out of the telescope that you could see. Now, in order to create a jet, you have to have something very energetic at the center of the galaxy. Now, if you take a telescope and zoom in, you can then see that the jet goes the whole way to the heart, to the core of this galaxy. And if you zoom in again, you can see that there's even more structure in there. So we're just getting these bigger and bigger telescopes, and we're seeing smaller and smaller detail until you find that there's a gas cloud in there. And this is a Lofar picture of a gas cloud in around the center of this M87 galaxy. And you can see these jets coming outwards. Now, this is an image then taken zooming in again with the Very Large Array, which is in Arizona. And you can see more kind of layers of this gas cloud. Again, this tantalizing jet. Again, you go in more and more. But this was the profound picture that I think was one of the most profound pictures of my lifetime. And that was a black hole. And I almost didn't believe it. I think it was a bit of a letdown in some ways, but if you think about it, that there's billions of masses of the star of the sun in there, and there's an event horizon, as the theory would have said. There's a black shadow of the black hole. There's lensed light from gravity bending light around. And using my advanced PowerPoint slide skills, this is kind of what you might expect. So it's very, very close to what the theorists and the cartoonists would have thought was in a black hole. And this is what telescopes do. This is what radio telescopes do. They allow human beings see beyond what we thought was possible. They allow us to test theories about the very origins of a universe, the structure of stars, the structure of galaxies. And that's why we do it as human beings. We've come out of our cave. We're looking up at the night sky. We're taking technological leaps forward, and we're trying to understand the world around us and the universe around us. And this is what got us in Ireland to build this low frequency array telescope and join this great European effort. And trying to do it. But along the way, we train students, and we are training students. We're developing IT skills, building supercomputers, testing big data, and also inspiring the next generation of astronomers and scientists and innovators, people who want to think big, people who want to think different. And I think that's really what astronomy can do. And that's what Bulgaria is also looking to do as well. There's a consortium led in Bulgaria by the Academy of Sciences that's trying to build a Lofar station in Bulgaria in a very radio quiet area. And that would stretch Lofar further south and further east in Europe and create an even bigger telescope and allow us make even more profound discoveries about the universe. So thank you very much. And here's to fingers crossed that the Bulgarian government eventually fund that telescope and join the big Lofar effort.
All right. Well, thank you very much, Peter. Fingers crossed indeed. I mean, we will be, extremely happy if a project of this scale, comes to life in Bulgaria. That would be awesome.
Absolutely.
Now, Peter, I'm just going to ask you if you could stop sharing the presentation so we can both see each other.
Okay.
Okay.
Let me stop sharing. There we go.
All right. Okay. And now I was wondering while I was looking at these extraordinary images, I couldn't help but wonder, how does an astrophysicist feel about himself while studying these things? Now, what do I mean by that? Now, we all know that every person who is at least mildly educated is aware how grandiose the universe is, and that sort of puts things into a perspective. But me not having to deal with that on a daily basis, I very easily go back to the sort of the natural state of things. I just keep on living my life. Whereas you have to think about these things all day. Does that bring any sort of existential angst or something? Or how do you feel
Oh,
about
wow.
that?
My God, what a difficult question to
Yeah,
get us
sorry about
started
that.
with. Yeah, it's funny that you say that. I was talking to my wife this morning. We were
Mm.
walking along the seafront, along by the Irish Sea, and talking about science. So she's a geneticist,
Right.
and I'm an astrophysicist. And we were talking about science, and I was talking about this talk, and I was saying, it's amazing to be building radio telescopes. It's an amazing thing to do, and it's amazing to see students come in and use those telescopes, and learn how to build them and how to analyze the data from them, but ask their own questions about the universe, and to kind of see them grow. I think that's really rewarding. And that's on a human level. I think everybody can understand that one. But I get giddy like a kid when I see a new discovery. I mean, I'm almost embarrassing. I get so giddy about some of the discoveries that we make. And you don't make many in your life. You may make one every 10 years that you're really, really excited about. But there are those moments where you go, oh my God, it's oscillating. Or, oh my God, it's doing what it shouldn't be doing.
Right.
Oh, maybe that theorist was wrong. And imagine how great it would be to say that Schrödinger was wrong or Einstein was wrong. There's something great about that. But also discovering things that people have never seen before is wonderful. I think in astrophysics, when you make an observation and you just have no idea what the hell you're looking at, that's kind of really interesting. And actually, when you and I were talking beforehand, you were asking about SETI and the search for extraterrestrial intelligence and so on. And it was a bit of a kind of a weird discipline when I was a kid. But nowadays it's real, and somebody will detect that signal, and the hair on the back of your neck will go up when you see that signal that says, hello.
Well, now that you mention it, let's spend a little bit at least of time on this topic. Now, I'm interested. Now, you see these enormous projects for studying the universe, observing black holes or solar flares and things like that are sort of they're empirically provable, so to say. They're practical in this sense, but very few or very little funding is going to projects like SETI, for example. For looking for sort of, let's say, technological footprint or something like that. Now, would you say that the current scientific culture actually hinders that types of research? I mean, is it looked upon, like, you know what I mean? Like, if you ask the question,
I think that if you speak in kind of financial terms, I think we as humans and we as governments and we as humankind should have a portfolio of investments. And you should have your solid kind of blue chips in there where you're doing the solid stuff, and you're doing your nanoscience, and you're developing lasers, and you're doing very applied research that has direct benefit to humanity. And that's really good. And there will be discoveries in there, no doubt about it, that are profound discoveries. But I also think that there's that area where it's kind of curiosity-driven research. It's where it's actually, I think it's what makes us innately human, as to why we want to understand the way something works. Not because of any immediate benefit, but we just want to know, and I think we should have a pot of money, a pot of kind of taking a bet, taking a gamble on something that's risky. And it could fail, and in all likelihood it will fail, but that's okay. We should accept failure. But failure is part of the process of discovery. But it's hard. We are all scientists who need to get jobs, and we need to pay the bills, and we need to buy houses and put bread, food on the table. So, sometimes people can be conventional. So it's hard. You need renegades, and actually, you need people like, I always think about, I like rock music. You need to look at, people who are going to disrupt in rock music where they come along and say, I don't like that. I'm going to turn up the volume. I'm going to turn the distortion on.
Yeah.
I'm going to play this faster and louder than anybody else has ever done before. And I'm going to break the rules. I think you need real rule breakers and scientists who are going to, if you excuse the expression, give two fingers to convention and just go forward and try and take a risk. But I think funding agencies need to match that ambition, that risk taking. And it's hard because funding agencies are then answerable to governments, and governments don't like that. Governments like to put in at 10 euros and make sure that a product is developed. And so governments aren't good at this. But I think that things like the European Research Council have actually, there has been a bit of a change in that. So the ERC is, a European community project, which is basic research. It's about curiosity-driven research, and they take a risk with what they do. And I think we need to keep doing that.
All right. So if we imagine a scenario in which someone speculates that, for example, this recent object that came from outside our galaxy, the Oumuamua, I think was it called? If there is a speculation, okay, this is an extraterrestrial object. It's made by an intelligent thing, or it doesn't seem like it's a natural object. Let's fund that. How fringe of an idea is that, and do you think that something like that will be funded? And I'm asking that because it was a specific question that was asked from a friend of mine to address. He's sort of a conspiracy theorist kind of person.
Yeah. But he's got to be proven wrong, or he's got to be proven right, and data does that. So you can't just, as scientists, you can't just say, let's not think about that. It's a bit uncomfortable. Being uncomfortable is kind of part of what it's all about.
Right.
With an object like that, though, it is controversial. I've read the paper actually a couple of times just to get my head around it. Mm-hmm. It is weird. It is a strange shape. Our convention hasn't been to create shapes like that. Most shapes are like that. I don't know if you can see that. No, you can't see it. But I have a ball behind me. That's the way gravity tends to do things. This is for my Christmas tree that I just didn't put away the Christmas ball. It's still in my attic. Right. But, that's what gravity likes to do with things. It likes to make them spherically symmetric. But this object wasn't spherically symmetric. It was elongated and it looked strange. So the inference was that, in that instance, one scientist said that maybe it was created by an extraterrestrial and it's a spaceship. Well, I haven't been to it, so I can't prove them completely 100% wrong or right. I think it's unlikely, but I think we should go and have a look. And actually, I was involved in a review panel for the European Space Agency a couple of years back, and we took a big risk on something where we selected a spacecraft or recommended a spacecraft for funding, and this is like €500 million, to go out and sit just outside the Earth and park and wait for these kind of weird objects to come. And when these weird objects are going to come, then Europe has a sentinel out there which will go out and then go and do an orbit around and go, what on earth is in here? Let's take a picture of this. Let's take a spectrum of this. Let's go and poke it and see what it is. And that's what we should do. And I thought it was a risky thing to do, but I'm glad we did it.
So just as a side note, we spoke before this conversation that you were a member of the Space Science Advisory Committee for the European Space Agency. So could you please share a little bit? How does the decision-making process look like? When you make decisions like that, because obviously we're dealing with public money here, and we have to get the most bang for our buck, so to say. This is at least what governments, I would assume, expect. So how does this work? I mean, how do you decide what to finance or not?
Yeah, it's tough. I mean, the European Space Agency is our space program in Europe. It develops launchers. Actually, here's one of their big launchers. I have all my props beside me here at the moment. So we have a little rocket, but it builds launchers. It puts spacecraft, satellites up into space that are then looking down at the Earth. They look at weather patterns. They look at shipping lanes. They look at plankton blooms. They look at very practical things. But also a portion of the European Space Agency's budget goes into space exploration, going to other planets, putting rovers out there, landing on comets, or testing Einstein's general theory of relativity. It does all of that. And it falls to the ESA and their engineering teams who are just brilliant to work out, can it be done technically? Can we actually send an orbiter out there, get it into an orbit somewhere in the distant solar system, get a lander down on, drill in through the material, and can we do that? Is it technically feasible? And you get a big report back that all the scientists then read on the panel. And then the scientists say, okay, well, yeah, it can be done technically. Now we've got to compare apples and oranges, and I don't have any apples and oranges to compare here at the moment, but we compare apples and oranges. But on the panel, you'll have a cosmologist, you'll have a high-energy astrophysicist, you'll have a planetary scientist, you'll have a solar physicist, and we will then review the proposals, and we'll get down to like a couple, maybe 3 proposals, and we'll then it gets hard because you can have strong personalities. But ultimately, we're looking for the best science for Europe. We want Europe to be the best in space science. And so that's really what we do. And I always remember the chair of a panel saying, be careful with this. This is taxpayers' money. We want, and think about it in units of hospitals. It's a $500 million or €1 billion. Now, it's not either or spacecraft or hospital, but it's that important. And that stuck with me. That, when we were sitting having dinner at night in Brussels or Paris or wherever we were, arguing over these missions, you go home exhausted after a couple of years of evaluations. But I think I've always seen the right solutions. There's lots of disappointed teams. I've been disappointed many times. Right. But I think Europe and European taxpayers are getting the right amount of money. And also remember that this money doesn't just go into space. It goes into companies in Europe. So companies then get to build detectors. They get to build gyroscopes. They get to build the communication systems. So it actually helps the European tech companies remain competitive, and then they can spin out lots of these technologies and develop services for European citizens, even though it may have been originally about general relativity. So there's lots of spin out potential that comes from European space exploration.
Yes, I mean, it's this spillover effect, from institutions like the European Space Agency is very often overlooked, as a general effect on not only on industry but education. For Christ's sake, I mean, it's inspiration, even if you will, to inspire people to move forward and seek scientific careers.
I should say that the European Space Agency has its first call in 12 years for astronauts. So if you carry a European passport, and you have a couple of other prerequisites, you can apply to the European Space Program to become a European astronaut. So great opportunity for all.
Even at the age of 35. I mean, am I out of the question now?
Hey, a lot older than you and a lot older than me. I must say, John Glenn in the United States was he in his 70s, I believe. Right. And I once, there's Lauren Acton is an astronaut who's also a solar physicist like me, and I remember having lunch with him one time, and he's colorblind and he's missing part of his finger. So there's hope for us all.
Right. Well, yeah. I mean, we are kind of used to the idea of astronauts being superhuman, but that changes now, yeah. So
well, it does help if you're a fighter pilot. It does help if you've got a PhD in engineering, and if you also have an MD in medicine. So these people who do go up, they are super qualified, and they're superhuman, really. They have to be just brilliant at doing everything.
All right. Let's go back to radio astronomy. We have, people are submitting questions here, so let's address some of them. First of all, can I build a working radio telescope in my backyard?
Yes, you can. I love that question.
Do you have instructions on that? I mean, can I find a video on YouTube?
Yes, you can. There's a project called Radio Jove. And what Radio Jove is, you can Google Radio Jove, and really what it is you get a wire, like you hang it up like a washing line in your back garden, and you connect it up to a little preamp and connect it into your sound card or your computer, and you can pick up radio bursts coming from Jupiter. It's that simple. There's also you can get an old TV aerial. And that's actually how I started in the field. Me and some PhD students maybe 14 years ago, because I wasn't actually a radio astronomer. I was more of a space scientist working on big ESA and NASA missions. But we just got a TV aerial, pointed it at the sun, and then bought this thing called Callisto, which is a small little TV tuner. And we tuned across the signal, and we were able to pick up radio waves coming from the sun. And in fact, we were also able to see the Milky Way going overhead. So you can do radio astronomy for very cheap. I mean, maybe it's a bit of a joke that you can say you can take a metal coat hanger and plug it into a preamp, but it's not far off. So yeah, you can go look. And I think that's what's lovely about radio astronomy, that you can do some things for very cheap. And it doesn't always have to be these super big things. Actually, just to say, when with my student, he's now a research fellow, Owen Carley and Pietro Zucca, we built some antennas down in Birr Castle 14 years ago with a technician called Joe McCauley. And actually we detected radio bursts. We saw some funny little blips in the radio bursts that told us that there was electrons getting pulsed out of a solar flare. And we wrote a paper that went into Nature Physics, and it ended up on the front page of Nature Physics. And I think the entire project cost 20 grand.
That sounds awesome. Okay,
Yeah,
so if we imagine then I built something like that in my backyard. You did show that Lofar is connected with other similar radio telescopes across Europe. Now, can we imagine like connecting that type of amateur radio telescopes across the globe, essentially, and will that be actually helpful if you connect them in a single net and look up in the sky?
That's interesting. A citizen science project around radio astronomy. Now, Callisto, which I mentioned earlier, is kind of a pro-am, professional amateur kit that people are using. High schools are using it, universities are using it, and they all take data, from India to Malaysia to Russia to, the United States to all across Europe, and that set of those data are all shipped back to, I believe, Switzerland, actually, and it's collected and scientists analyze it. So that is very much a huge citizen science project. But there are other ones as well. There's one called Super SID that I've actually used, and Super SID is a very low cost VLF receiver, so very low frequency signal, and you can study the Earth's ionosphere with it, and it costs about, I'd say €100 to build. I've built them. Actually, during lockdown, during COVID, I built one in my back garden, and we're taking data with it. But it's a couple of plastic tubes with a wire wrapped around it 20 times, and then plugged into this receiver that you can buy online for the total thing, 200 quid or €200, and all of those data goes back to Stanford in the United States, where people are studying the ionosphere. So there are a lot of little bits and pieces that can contribute to global professional science.
Right. Now, speaking of Lofar specifically, can you also beam signals from it, or you can only receive?
No, we can only listen with Lofar. We don't have the equipment in order to send a signal out. Now, of course, the Arecibo telescope, which has really had a tragic occurrence recently where part of it collapsed. That telescope is 300 meters or something or so across, and it's just very, very heavy in a small valley, actually. But part of it collapsed. The main kind of kit of instruments collapsed, and it fell down on top of the telescope, damaging it. They're looking to repair it, but that could detect and transmit, which was interesting. And it could transmit because it was trying to bounce radio signals off the Earth's ionosphere and then listen to them. But really interestingly, during my PhD, I was working on a spacecraft called SOHO, which was an ESA NASA mission. But the engineers were doing a spin maneuver, and they lost contact with the spacecraft. So you got a €1 billion spacecraft tumbling through space, and you no longer can talk to it. Imagine how you would feel that night. So what they did with Arecibo was they used it as a radar, and they started pinging into the sky where they thought Soho was,
Right.
and were able to eventually work out where it was and how it was spinning. And then once they knew where it was spinning, they were able to start beaming to it and saying, hello, 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 hold on, warm up, no, turn that on, turn that bit off. And they eventually got the spacecraft back under control, and they were able to point it back at the sun again. But there are very few communications kind of projects out there where people are beaming out messages, for example.
So, what is besides the fact that you cannot beam signals? What are the other main differences between the just mentioned Arecibo and the Lofar project? I mean, what are you...
Yeah, I mean, Arecibo is it's as I said, I think it's 1,000 feet or just over 300 meters in diameter. It's so big, it just can't move. So all it does is it looks straight up.
I remember Pierce Brosnan like sliding through it, in one of the movies. So yeah.
Absolutely, yeah. He did actually. They had a lovely battle up at the
right
up at the instrument focal plane.
And
actually,
Sean Bean died again. Yeah.
yeah. I gave a talk at Arecibo about 6 years ago, and they offered me to walk out to the focal plane, but I'm terrified of heights. So I'm not applying for the ESA astronaut program, and there's no way I was going out to the center of that thing. And particularly since it's collapsed now, I'm glad I didn't. Yeah, so that's one of the problems, that you just can't move it. With Lofar, you drop these antennas all across Europe, and you use software. Even though the antennas are like this, you can put a computer in between them, and they effectively point using software. So you can point all around the sky with software, and also you can take an all sky picture, whereas with Arecibo, you couldn't take an all sky image. So with Lofar, if you want to look for, say, transient things, and it's actually about that serendipitous discoveries, if you want to just be looking at the sky or listening to the sky, I guess is a nice analogy, you can just open up Lofar, open up all the antennas, and listen to the night sky. And that's where you can see the pops and the wiggles going on and try and make discoveries. And there are these things called fast radio bursts, which are just these radio bursts that were just happening. They were just popping off, and nobody knew what they were. These are discoveries that are made in recent times. But, it's a big question now. How are they made? Where do they come from? What are they? Are they exploding stars? Are they the collapsing cores of galaxies? What are they? And an instrument like Arecibo can't make that discovery. But what it can do is it can point very accurately at a pulsar and then follow its pulse with great sensitivity. So that's the kind of thing there are different tools for different jobs, and that's really what they do. And together, actually, they can do some interesting things as well.
So are you are there actually plans? Because right now we know this that there is a Chinese project going on, for a huge radio telescope as well. Are we looking into some sort of a cooperation between the different radio telescope programs that we currently have? I mean, what is the politics of this whole thing?
Oh my God! You want an Irishman to talk politics to you? Yeah. The politics are there's competition. There's surely competition between Europe and the US and China, primarily. Of course, India wants to put its mark on the moon and on the space programs, and Japanese and so on. We all carry our national flags with great pride. But I think we also understand that you can't do big astronomy without cooperation. So a project like the Square Kilometre Array led to governmental or intergovernmental negotiations and signatures at the highest levels in government to cooperate on radio astronomy. And the Square Kilometre Array involves European nations. It involves South Africa. It involves, I think Brazil is involved in it, and then of course Australia is involved. So many nations involved, but they'll build the telescope partly in Western Australia and partly in South Africa and neighbouring African countries as well. But it's about cooperation. With the FAST telescope, that's primarily Chinese. There are many European collaborators on that. But as a nation, they want to make their mark, and they're making the lead at the moment. And it's up to us in Europe to keep up, catch up, and overtake.
Yeah.
That's competition's a great thing to have in anything. With competition, it does drive innovation.
Right. Now, Lofar is obviously an international effort, an international project, but when it comes to sort of local science, so to speak, I mean, is there sufficient or any time given out to sort of like local science projects from, for instance, someone from Dublin University? Can they use the Lofar array for observation in a similar way that some optical telescopes are being used, public?
Yeah, that's an important question for Bulgaria, I guess. Why build this radio telescope? Why should we build a radio telescope? Well, the way it works is the more Lofar stations that you build, the more time you get on the total telescope. So if Bulgaria builds one that costs 2 million and the total thing costs 150 million, you get that fraction of time on the total array. And that was really because Bulgaria, and most countries aren't going to spend 150 million euros on a radio telescope. So to get into the club, you get enough time and enough data. So in Ireland's case, I think we get 2% of the total array at time, and that's enough data to keep us busy. The other thing is, though, you get to use the small radio telescope on its own for a couple of days a week. And that's really important time because you then give it to a PhD student and say, go play, go try something, break it. I love telling PhD students to break it because if they're breaking it, they're trying their hardest to do things that they shouldn't be doing. So I want them to try and push, and that's where training comes. That's where if you don't have it in your back garden, you can't play with it. And to build it and to control it and to analyze the data from even a small one is really, really important for training PhD students. And I think that's one of the great benefits of having your own Lofar station.
Yeah. One of the most pressing issues that we are currently facing, or at least scientists and astrophysicists in particular that are observing the sky right now are facing, is the overcrowding of of the lower Earth space, so to say. We're talking about Musk's Starlink, the constellations of satellites, and the more overcrowding that we are seeing that is going to be happening in the recent years. Now, how is this going to affect radio astronomy? I mean, obviously it has a negative effect, but how significant that effect actually is?
Yeah, we're still trying to get a handle on that. This is all new for all of us. I think for optical astronomers, it's clear, these things, if you launch lots of satellites and they've got reflective surfaces, they're going to flash, they're going to reflect sunlight and they're going to ruin images. That's a certainty. What I think is really difficult is, international treaties or government treaties or government regulations around this. So, can anybody just put them up? And the answer is at the moment, yes, you can. So, you could imagine a horrendous situation where somebody puts up their favorite drinks sign up there and pollutes the night sky for us all.
Right.
At radio wavelengths, the SpaceX are trying to launch ones that give you internet communication right across the globe, and it's supposedly affordable. It's actually not that affordable, particularly outside US type of salaries. But they're going to broadcast back down at gigahertz. So any radio telescope that's working at gigahertz is going to have some problem. So that's microwave. And for us at low frequencies, we don't see them at the moment. They may become reflectors. We're not really sure about that. Certainly we see aircraft, just standard aircraft, and we do see, the International Space Station, we'll see it because a radio wave that goes up gets reflected off them and then it gets reflected into our beam. So they may become reflectors. And without some kind of legislation around what you can put up there, you'd have to be concerned as a citizen, never mind as a radio astronomer, that there is some kind of regulations and international treaties that give you parameters on what you can and cannot do in space. Excuse me. And once all of this is done, then who's responsible for bringing it back down, and where does it come down?
Yeah.
There's all of that kind of stuff that's important.
Yeah. And, international regulation is famously hard to achieve, so you're going to have to wait
Absolutely.
probably. And now they're just painting them black. I don't know how how fixable that is, but
Yeah. Well, listen, they should have thought about that earlier, but it's
yeah.
not the only solution, and it's not 100%. It's not 100%.
All right, so working on Lofar now, I mean, what is the question that you are specifically looking for an answer to? I mean, what is keeping you awake at night?
What is keeping me awake at night? Keeping the funding going.
Yeah. It's always the mundane things.
Yeah. Keeping the budget, keeping the tax man away. But no, I mean, there's a couple of projects that are really cool that we're working on at the moment. And it's kind of a new area for me, is we're looking at the way the sun interacts with planets. So, the sun has these explosions that go flying through space, and they hit other planets in the solar system. So one of the things that we're doing with the Irish Lofar station is it's moving through space, and it's hitting Jupiter and Saturn. And once the solar wind hits Jupiter and Saturn, the aurora takes off on those planets. Also, you can get their magnetic fields are changing as well. So we're trying to understand the detailed link between the sun and these planets. But what's interesting about that is, when we were kids, there was 9 planets, and now there's 4,000 planets that we know of. So understanding how stars interact with planets is really important, because we're finding more and more of these planets. And with Lofar, you can find planets that have strong magnetic fields. And now people have got tentative results for that. But I think that's going to be really interesting. Can you find a small rocky planet that's not too hot, that's not too cold, that has a magnetic field, and then we go looking? I think that is a really, really fascinating thing. And I so you're too young to remember the moon landings. I'm actually too young to remember the moon landings, and I'm well through my career. But that was a moment for a generation, human beings putting a foot on another body, putting a foot on the moon. What's been our moments? I don't know. I don't know what our moments have been, but imagine if we found a small rocky planet that had life on it. That might be our moment. That might be the moment that we say there's a biomarker, that might indicate life, or there might, even more than that, there might be intelligent life. That kind of thing, I think, has to happen in our lifetime. I think that has to be the next step, and that's going to make us feel small. I think we're gonna it's going to have a profound effect on our psyche, like the moon landings did. So I hope we have that moon landing moment. But just you asked me about what's keeping me awake at life at the moment. So that's one of the things. But there's another thing that's kind of a new field to me, and that's looking at these really compact. So when a star evolves and it burns out its fuel, it gradually collapses and collapses and collapses and collapses until it becomes really, really compact. And then it's kind of like a pulsar, but it can have glitches. It doesn't tick at like an accurate, 100% accurate clock. There's glitches in it, but we've observed some of these glitches in the Crab Nebula, actually. And we don't know why there's glitches. Is there matter falling into the pulsar? Are there episodic kind of explosions that are happening on the pulsar? We don't know, and that's another really interesting one. And it tells you about a pulsar and its environment, a very ancient star and its environment, and how they interact with one another. And one of my grad students, Dave McKenna, is working on that one.
I mean, these are really profound things. Now, you've been heavily involved in studying the sun. Actually, you did say that this is your field of study. So, are solar flares gonna end us all, or is it gonna be something else? We had an event recently on solar flares, and it did sound scary, to be honest.
Yeah, I love this question, and this is this is another thing that I'm really concerned about. There was a paper that we read in my group's journal club last week that was looking at the worst case scenario. how bad. The biggest flare that we know of happened in 1859. It's called the Carrington flare. In 1859, nobody needed to use their mobile phone to get to Starbucks, right?
Yeah.
Nobody was getting self-driving cars that were going to deliver things around the continent. Nobody was, expecting that they could get GPS or timing signals or whatever.
Right.
What happens if something like that happens nowadays? We know exactly what's going to happen. It's just not going to be good. You're going to lose communications. You're going to lose shortwave. You're going to lose GPS. You're going, it could even be that a power grid goes down. And if a power grid goes down, then we're really suffering. Because within 2 or 3 days, then your backup diesel generators aren't working very well at your hospital.
Yes.
The life support machines are failing. I mean, this is awful stuff. But I didn't think we'd have a pandemic this year. I thought it was a low probability. But it was a low probability, high impact event. And if you look at people who study risk, these kind of space weather events are being studied. They're low risk, high probability. But the paper I was studying last week was looking at the likelihood of it being worse than Carrington, that Carrington actually isn't as bad as it could be. And they think it will be. They think that there could be a solar storm that could be far worse than the Carrington event. And if that hits, then we really are in real trouble. And how do you get around that? I don't know. Well, number one, the odds are low. Okay, so the odds are for one of those big ones, for a Carrington, you might be talking 1 in 100-year events. So it might be uncomfortable. Railroads signaling may not work. GPS might be interrupted for a little while. But if you had something that was 10 times Carrington, then you could end up with transformers being burned out. And if transformers are burned out, then we're all trying to buy them from the Chinese who are making them in bulk and making them cheaply. And then the first guys who are going to get them, I guarantee, are going to be the biggest countries, and the rest of us are going to be waiting. So
that sounds familiar,
yeah, it's incredible. I'd write this in the beginning of my proposals the whole time, and I kind of became blind or deaf to it because I kind of stopped believing how important that is. But it kind of renormalized my understanding of probability and how important it is to understand this. Now, I guess the corollary to that whole question is, what the hell can we do?
Yeah.
So I think as a space scientist, we can give you better weather forecasts. You'd like to know when there's a hurricane coming. You'd like to know when there's lightning or a bad weather warning happening on the Earth. It's equivalent to that. And then emergency, there are offices of emergency planning in all of our countries who have scenarios that they can follow, and they work out, here, if it's a small one, we do this, or if it's a big one, we do this. And then there's a red phone over there where we ring the president. So they do have protocols for these kind of things, but we need to take them seriously, and we need to look at them even if they're low probability.
Right. I don't know. I mean, go.
We shouldn't end on this.
Yeah. We shouldn't end on this really. But I mean, are you optimistic? I mean, there is a lot of talk right now that people are sort of that science is returning its respectable place in civilization now that people realize that scientists are actually going to save our lives, so to say. Speaking in terms of the coronavirus, of course, and the vaccines development and etc. Are you optimistic that we as collective societies are actually going to put some more emphasis on scientific research and prioritize it a little bit more than we actually do? Because there seems to be a lot of very speedy developments going on right now. I mean, we are seeing space programs are exploding, but at the same time there is a general feel of stagnation, to be honest. Despite all the space news that we are receiving, and it feels like science is kind of slipping at the outskirts of culture. So are you optimistic that we as a civilization will put it back into the center, if it ever was, actually?
Yeah, if it ever was. God, that is definitely the most difficult question that you've asked me, and it's one that I've grappled with for a lot of my career. and my life as to, why invest in science? Why should governments have to make decisions between a new road, housing, and some guy who wants to study a black hole, or some girl who wants to study a planet?
Yeah.
It's really, really hard. And I think the budgets that go into science are low at the moment. They should be more. And I think one thing that we've learned from the pandemic is that having that reservoir of good scientists who actually are working on the cutting edge, are ready to deal with these things, and if they're brought together and organized and funded, they can actually address some of the big problems. I mentioned my wife earlier there, and we were talking again this morning. She's actually a bat biologist who has worked on diseases in bats. She would be of the opinion that and very much looking at viruses and the origins of viruses and how they're transmitted and so on. But, there's no immediate application to that 2 years ago. There is now. And I think I don't want to be in this situation where I told you so around a geomagnetic storm. You don't want to be in that situation. You do need to have people who understand some of these more maybe exotic things, but also, when Einstein was the person who came up with, he didn't get a Nobel Prize for relativity. He got it because he realized that if you've got, a piece of metal and you fire, a photon onto that piece of metal, that an electron will come out of it. It's called the photoelectric effect. And it's the basis for so much of our, detectors around us that are, a motion sensor is using some of this. Modern electronics is using that. When Schrodinger was doing his wave mechanics, I was drawing psi there, by the way. When he was doing his wave mechanics, he didn't really think that quantum tunneling of electrons across a barrier was actually going to be useful in electronic devices and miniaturization and nanoscience. But it was really important that these guys had Princeton Institute for Advanced Study, where Einstein there was money, there was an environment, there was a place for him to think. Erwin Schrodinger came to Dublin. He came to the Dublin Institute for Advanced Studies, and he worked here for 15 years. But there was a place, there was a government program there. So it really is incumbent on governments to have these kind of places available where people can think freely and deal with some of these issues that may have no benefit initially, but in the future they will. And I'll just give you one more example that it is very close to my heart. In DIAS has an observatory called Dunsink Observatory that I'm actually director of now. But back in the 1850s, a guy called William Rowan Hamilton was working there. He invented the Hamiltonian. He was walking along the banks of the Royal Canal in Dublin, and he had a flash of brilliance. He described it as a circuit closing in his mind, and he wrote some equations on a bridge called quaternion equations. Now, if you like 3D gaming, if you like special effects, if you like navigating spacecraft, you got to get your quaternions right. But there was no application for quaternions between 1850, when he wrote them on the canal bridge, and about 1960, when space programs started up. So, it's very hard for somebody to write a proposal saying, I want to do something, because nobody knows the answer to it.
Right.
And I think that's what we have to fund. We human beings don't know the answer to it. We got to work it out.
I mean, that's it. Well, okay. Well, thank you very much, Peter, for this, for the fascinating talk and for giving us the opportunity to ask our questions. It was really
Pleasure.
nice, and I want to wish you, all the best in your work. I mean, God knows it's important. So, I hope everything goes smoothly with Lofar. And I wish you, of course, lots of health. This is what we all need now. Yeah.
Absolutely. Thank you very much for inviting me along and for the fascinating conversation. Sure. And here's to Lofar, Bulgaria. I hope it happens, and anything I can do to help, my number.
I'm sure they will reach out. I'm sure they will reach out. All right. Thank you very much, Peter. I'm going to ask you to stick around for a few more minutes for I just gotta say a few words. Okay, ladies and gentlemen, thank you very much for staying with us up to the end. Now, as you know, by tradition, what is coming next. I'm going to ask the technical team to give us the visuals here. So first of all, of course, we would like to thank the European Space Agency for their generous support of this event and all our space events that we are doing here at Ratio. Thank you very much for this. We also want to thank, of course, Club Melon, which are our sponsors for a few years now. So Melon is a software company that is also very unconventional in the fact that they actually support science communication. So thank you, Melon. Melon is actually looking for talents. Like I'm pretty much convinced that there are plenty of those watching right now. So you can check out Melon if you want to, find a new work. What is coming up next on the 16th of March, live stream again at 8 o'clock, we will be talking about Mars, our new home. It's going to be a fascinating event, again, fascinating talk. So if you're interested about the future of human civilization and about the future of Mars colonization, you can join us again at 8 o'clock on the 16th of March. Again on YouTube and Facebook. You can see our events that we've done previously on our website /videos. You can check out the topics about space debris. Again, a few topics about Mars. So check out what we've done in the last few years. And of course, if you are more of an audio person, you can listen to our podcasts. And you can find them also on our websites. So what else do we have? We have, of course, to thank our supporters from Patreon.com. Thank you very much, guys, for supporting what we're doing. And if you want to support us as well, you can go to Patreon.com/RatioBG. We're going to add you to an exclusive Discord server where we can, you can chat with our team, give us recommendations, advice, or just have a general talk. Check out our website, our YouTube channel, subscribe, and follow us on every social media for our next events. Thank you very much for joining us, guys. This was all for tonight. I was Petko. Have a good night.